All right, I guess we're ready to go then. All right. Hi, folks. My name is Chelsea Troy. I am an engineer here at Mozilla, and today I'm going to talk about the approach we're taking to data automation around search terms. So to do that, I'd like to start by sketching the landscape we're working in and explaining where data automation fits in for us as an organization that has built its value system and, frankly, also our reputation on data privacy. Your privacy, the privacy of anyone using Firefox, is extremely important to us. And we're in the browser business, which tends to pit sustainability against accessibility. We need revenue to keep making and maintaining the browser, and we can achieve that either by charging for it or supporting it with clients, namely that's advertisers. Lots of content websites run into a similar predicament. Ads keep the internet free, and we don't want internet content or tools to become a luxury good. But delivering useful ads requires data about what people are searching for. So how do we balance constituent privacy and gathering data to deliver useful information for advertisers? Two ways. First of all, we make data collection opt-in. We only save search data if you have explicitly permitted us to. And currently, you can only even turn that on when the browser geography is set to the US English-speaking, Canada English-speaking, or Great Britain. And that's for reasons that I'm going to get into later. Search term data collection ships in the stable version of the browser turned off. Now, it does ship in the pre-release channel, so that's Firefox Beta or Firefox Nightly. It ships in those turned on. But if the terms beta and nightly don't mean anything to you, you have the stable version of the browser, and this is turned off for you unless you have changed it. To turn it on or off, you can go to Firefox Preferences and then Privacy and Security, and you can toggle the checkbox called Improve the Firefox Suggest Experience. So that's the first thing we do. Second, we sanitize the data. That is, we remove anything you search for that might contain personally identifiable information. We sometimes call this PII around Mozilla, but I won't be calling it PII today. We don't send personally identifying information to advertisers. In fact, we don't even store it long enough to use it for our own product research. Now, what does personally identifiable information mean to you? The answer might surprise you. It's not something like, does my girlfriend love me? Or why is there hair growing on my tongue? People type like their addresses into search bars sometimes when they're looking up directions, or their own name to see what comes up. We call that a vanity search. Or they paste their credit card number or social security number into a search bar. We think this is usually an accident. So we have a system for removing searches that contain personally identifiable information from our data. Even if someone has opted into search term storage, if they type something that looks like personally identifiable information into the search bar, we try to remove that before we store it for very long. We have a job that runs once a day in our stored search data to do this, and it looks something like this. That sanitization effectively separates what we think includes possible personally identifiable information from sanitized search data. So what does sanitization look like for us? Our data science team conferred with our legal team, and then they also analyze risk factors for personally identifiable information in search data. Two Mozilla data scientists, specifically Rebecca Burway and Dave Zieber, did an excellent data club talk a few weeks ago about that. So Mozillians should go take a look at the recording from that. I'm going to fast forward past the nuts and bolts for now and tell you what we do. First of all, we don't store your identity with your searches at all. And then second, from the search terms we get, we remove anything with the @ symbol in it, or a numeral, or a name. Now, you'll notice something about this strategy. It's extremely conservative. It removes all email addresses, credit card numbers, all street addresses with numbers in them, all vanity searches. But it also removes, for example, if someone searches recipe for lemon bars with less than 4 grams of sugar, that's out because there's a numeral in it. Food trucks attending paintings at Point Park because there's an @ symbol in it. We also remove Vince Camuto boots because there's a name in it. Those searches, you'll notice, all indicate that someone might be looking to do something or make something for which an ad or a coupon might be a welcome offer. But we don't know that because these searches contain numerals, the at symbol, and a name. But that's not our only accuracy concern about this strategy. Suppose we expanded the search storage opt-in outside of the regions we have it in now. We're not sure how accurate our name identification strategy would be for names or even characters that get underrepresented in search data that was used to train our name recognizer. It's also a safe bet that in the US and Canada, or most of the UK, that addresses contain numbers, but that's not a safe bet everywhere. So to do a better job at this for a wider audience, we might need a more sophisticated strategy than the one that we have right now. That strategy might include a variety of data automation tactics, fancier entity detection, more precise character stratification, or additional machine learning models. And those might be off the shelf or custom. And those things might help us better generalize to a wider audience. The thing is, with our current strategy, it's pretty easy to predict and explain what gets removed from the search data. With a more complicated strategy, things get harder. And there are several ways that more complicated data automation strategies can go wrong. We looked at some examples of search terms that would be removed before storage despite containing no personally identifiable information. Those are called false positives. And their consequence in our case is the loss of useful information because people doing the searches were, in fact, looking for things that the right ad or promotion could help with. An example would be the Vince Camuto boot search that we looked at earlier. We've also talked about how the current approach might not catch all the names and addresses outside our current context. Those are false negatives. And specifically in our case, they're an example of generalization error. Our approach was designed with a specific body of training data in mind, and it might not work on a different body of data that the current approach didn't consider. Their consequence in our case would be accidentally storing personally identifiable information, which is a thing we absolutely do not want to do. When your data automation strategy gets more sophisticated, these kinds of issues don't go away. They just get harder to catch. And we want to be proactive about detecting those issues. So we put together a pipeline for monitoring our data automation strategy and the data it operates on in production. This kind of model monitoring and data monitoring allows us to catch problems with our approach, and it's a good idea to put in place for any data automation happening in a production environment. But our case is a little complicated. The reason is that, as we've discussed, most of the unsanitized search data is not stored. We do keep a small amount around for a short time for reasons I will get to eventually in this talk. But how do you monitor data that you're deliberately not storing? That's what the rest of this talk is about. So here's a diagram representing our pipeline right now. This looks like a lot of boxes. Don't worry about it. We're going to go through it. This part you've already seen. Now we're going to talk about what happens after, after we sanitize the search data. So the sanitized search data allows us to work on our own products like Firefox Suggest, and it also allows us to work with our partners on ad content. We keep sanitized data in a table for 30 days. So we're still not keeping it forever, but we do have a few weeks to do any analysis that we need to do. The search term sanitization job metadata aggregation part of this diagram happens in the same job that sanitizes the data. It collects aggregate metrics about all of the search terms it's seeing, so those containing personally identifying information and not. And it delivers those aggregate metrics to a table. I'm calling these search volume aggregate metrics in this diagram, and the only reason I'm abbreviating it is for the sake of fitting it into the boxes on this flowchart. I leave the full phrase in documentation or anywhere that I have space to make those documents easier to follow for people who need to get up to speed. So you won't see SVAM everywhere. Anyway, search volume aggregate metrics. What do those look like? Here's the schema on that table. There are roughly two types of info in here. The first type is data on the job itself. Did it succeed? When did it start and finish? If it failed, why did it fail? Plus any implementation notes. All of this information has drastically reduced the amount of time that it takes us to debug issues with the job, and it has almost eliminated the need to repeatedly rerun it in order to identify whether problems got fixed. So it's really useful information to have there. The second type of info is what you came here for, which is metrics about the aggregate search volume processed in the job. How many search terms did the job process? How many terms contained the @ symbol? How many contained numerals? How many contained a word or a phrase identified as a name? How many were removed total for any of those reasons? What was the total count of characters, words, and uppercase characters? We can use this information to understand whether the kinds of things people are searching for are changing. We also include how many search terms included a US Census surname. We don't remove terms based on this because the surname list includes a lot of words that are most often used as actual words, like brown or black or white, or even some articles. But we can track how much these are used, again, to detect changes and also to monitor the efficacy of our choice to leave that data currently in the sanitized table. Finally, the table stores approximate language proportions, the value of which is a stringified JSON object whose keys are language codes like EN for English or ES for Spanish, and whose values are the number of search terms with more than 5 characters that a language detection model labeled with that language code above a confidence threshold of 0.2. Now, we know this is not going to be completely accurate. We ran a couple different manual tests and some heuristics to alight on that approach. It's accurate enough to detect large changes in the proportion of languages that people are searching for. The value of this column is a JSON object so that if language codes that we haven't seen or columnized yet join the data set, those will show up in the data. We have a separate virtual view in BigQuery that grabs this JSON and populates a table with a job identifier, plus each language code for that identifier and the count of that language code for the job. So it is tabular somewhere for easier searching. Now, that aggregate info includes the minimum information we need to know to detect changes in the overall data in such a way that we don't store or risk compromise on sensitive data itself. That's why I can show you a preview of that table and then post it on YouTube. Once we have that information for each job, we can compare the info in each job to that of past jobs. So our sanitization job data validation metrics table contains, for those of you from data science land, all the figures you would suspect it contains. We use percentages rather than absolute counts so that the size of the job, which is impacted by how often we run it, would not cause these numbers to change on their own unless we choose a cadence that like slices some asymmetric multiple of some kind of temporal cycles on what sorts of stuff people are searching for. For example, if we did an hourly cadence and people search for uppercase stuff more often in the mornings, then those numbers would change from row to row based on that. We haven't had that kind of issue so far, but example columns in this table include the percent of the search terms in this job that ended up getting sanitized for any reason, the percent that were sanitized for any of the 3 reasons we've identified, the percent containing a surname, and the average number of words across all search terms. The values here are all floats. We make use of their floatiness in the next step, which happens roughly here in the diagram. Again, Dave Zieber and Rebecca Burway developed a strategy for identifying concerning changes in this data. We compare recent rows to a whole bunch of past rows in 2 ways. First, we calculate the range of values we expect for each metric based on a historical window and bracketing percentiles on the top and bottom. The window size and percentiles are configurable in the job, and I'll show you what that looks like in the resulting table in a second. Then we do the same thing, but for a rolling average over some window of prior measurements in addition to the range. That rolling average window is also configurable. We compare a test window of recent values to historical metrics. The size of the test window is, you guessed it, also configurable. There's a general practice that I've employed all over the place here that I want to address directly because it runs contrary to some interpretations of best practice. A lot of these tables include both data about the search terms and data about the procedure run on the search terms. The search volume aggregate metrics table, for example, included whether the job succeeded, why it failed, and how long it took, plus implementation notes. And this data validation reports table includes information about how the comparisons are configured. For example, the number of days in the moving average window, and the number of days in the look back window, and the number of days in the test window, as well as the actual percentiles used. So you can see in these calculations, for example, in the 4 columns on the far right, we calculated our means and ranges for the 2.5th percentile and the 97.5th percentile. Some interpretations of best practice would say that procedural info like this should be omitted from the results table and left either in the job logs or put in a separate table for organizational purposes. In practice, I have found that the vast majority of the time, when a data scientist or a data engineer is looking at data about how a job ran, they're cross-referencing that info against the result. So empirically, having these two types of info in the same place has made developing and debugging these jobs extremely easy in some cases. So I recommend considering it depending on your use case. Anyway, this table also includes a column called range alarm. That column houses a Boolean value indicating whether or not any of the values in the range test vals column fell below the range low or above the range high value. The table has the same setup for mean alarm. Then we have a dashboard in Looker called What's in Search Terms as a Whole. That dashboard shares tabular and chart representations of search volume aggregate metrics and the validation report data. This that you see on the slide is what the top of that dashboard looks like. And here's what the bottom looks like, which is not critical to our discussion right now, but I really like the languages chart because I'm a languages nerd. So it made my soul a little sad to leave that out. And these days, I think our souls deserve all the little treats we can give them. So I'm showing you this languages chart. Anyway, the important thing is Looker has 2 alerts set on this table, one of them for the mean alarm and one for the range alarm. Fun fact, Looker actually only lets you put alerts on numeric columns. So this Looker view has a calculated metric on it for each of the alarm columns, which I have creatively named numeric version of mean alarm and numeric version of range alarm. And the whole calculation is that there's a 1 in that column where the respective original column says yes, and a 0 where it says no. And the alerts key on that. So that's how you do that in case anybody else ever has to do that. If one of these alerts is triggered, it emails all interested parties. Currently, that's the data scientists working on search term standardization. And then I'm also in there for good measure since I'm sort of the mechanic on this race car, but chiefly they would be looking at it. We don't have a staging Looker setup, so I temporarily set up an alarm on the production dashboard that tests for the nominal case, just so I could show you what the email looks like when a Looker alert triggers. It looks like this. It tells you which alert triggered and why, and it shows you the view that contains the alert in Looker. Then it gives you a button to navigate to the dashboard. So this is our minimum viable data monitoring setup. That alert prompts the data science team to manually investigate what's going on. Remember earlier when I said I was going to get to the reason that we store a little bit of raw unsanitized search term data. This is that part. We have 48 hours worth of search data saved before we remove anything. For exactly this purpose, just enough to support an investigation of this kind where we need to figure out whether something's going wrong in our data automation approach. Here's a more detailed and recolored version of the diagram for Mozillian interest, explaining where we keep everything. Designers, look away. I know this color scheme is an affront to your eyeballs, but it's a useful map should someone need to find something. I've got actions by constituents in yellow. I've got tables in BigQuery in pink. I've got the job that we run from a cron on Google Kubernetes Engine in green. Everything in blue is a BigQuery ETL virtual view. Everything in orange is a job we maintain in Docker ETL. And everything in purple is in Looker. Now, the reason that sanitization lives in Google Kubernetes Engine instead of the Docker ETL repository where we keep the vast majority of our jobs is that that job deals with unsanitized raw search terms. Docker, specifically Airflow, which coordinates our Dockerized job runs, doesn't have access to sensitive data tables. And we didn't see an easy way to give just this job access rather than all of Airflow. So we did this instead. The idea is to ensure the integrity of our models without compromising data security. So we've optimized a little differently than the standard data-driven approach, which is roughly hang on to as much data as possible. Instead, we've put a process in place to derive maximal insight from minimal data. And that allows us to monitor the validity of the assumptions that undergird our data automation while remaining true to our data privacy values as an organization. So